Have you ever gazed at the night sky and wondered about the origins of the universe? Not so long ago, we humans had no clue about those glowing objects scattered in the cosmic canvas above us. But as our knowledge advanced, we realized that most of these objects lie within our very own galaxy, the Milky Way. And the concept of an expanding universe brought us to the doorstep of the Big Bang. But what if I told you that the Big Bang was not the beginning? That there was something before it? Something called cosmic inflation? That's right. This mind-bending theory suggests that before the hot Big Bang, our universe underwent a phase of exponential expansion. And this theory of cosmic inflation has helped us solve several mysteries that the Big Bang alone couldn't explain. But it also left us with new puzzles, new questions that are still waiting to be answered, like the existence of primordial gravitational waves or the exact degree of flatness of our universe. Isn't it thrilling? But the most intriguing part is, you'll find out in a jiffy. What's up, my amazing and curious folks? I am your host, Cesar, and with me is the ever-enthusiastic Sonia. Are you ready to dive deep into the mysteries of the universe on the Curiosity Wonderland?
Hi there, everyone. Super excited to be part of this amazing journey with you all.
Don't forget to subscribe to our podcast and hit the bell icon to stay updated with our latest episodes. Let's unravel some mysteries together, shall we? Let's take a step back in time to when humans could only marvel at the stars and planets in the night sky without any understanding of their origins or composition. Imagine that for a moment. The moon, the stars, the planets, the nebulae, all mysterious points of light in an endless expanse. But as time went on, our understanding evolved. Now, we know that nearly all the celestial objects we can see with our naked eye are actually within our very own Milky Way galaxy. And with the help of more advanced tools, we can observe trillions of galaxies, each expanding away from the others. The farther away a galaxy is, the faster it's moving away from us. This observation of an expanding universe led us to the concept of the Big Bang, the explosion that gave birth to our universe.
Wow, that's fascinating, but you mentioned earlier something about the Big Bang not being the beginning.
That's right. Just when we thought we had it all figured out, our understanding of the universe's early stages took another interesting turn. We began to consider the idea that the Big Bang might actually have been set up by an even earlier phase called cosmic inflation.
So, we're talking about a series of universes, each separated by expansive space. And our universe is just one of those bubbles?
Exactly. The idea is that one of these bubbles, where inflation ended, gave birth to our universe about 13.8 billion years ago. And though our universe started with a very low entropy density, the second law of thermodynamics was never violated. But let's not forget the Big Bang itself. After the initial conditions set by cosmic inflation, the universe started as a very hot, dense, and uniform state. As it expanded and cooled down, it gave rise to protons and neutrons, atomic nuclei, neutral atoms, stars, and galaxies. And within these galaxies, the formation of heavy elements, rocky planets, and even life became possible.
This is all so mind-blowing, but it leaves me wondering, if the Big Bang wasn't the very beginning, what was?
Well, the Big Bang couldn't have been the very beginning of the story. There are still some physical puzzles that remain unexplained, if we insist on that.
You know, this whole discussion about the universe's beginning and its complexities reminds me of a personal moment from my childhood. When I was about 6 years old, my father bought me my first telescope. I remember the excitement of setting it up in the backyard and waiting for nightfall.
Oh, I can only imagine your anticipation.
Yeah, it was like waiting for a grand premiere. I remember the first time I peeked through that telescope. My heart was pounding as I adjusted the lens, knowing I was about to witness the vast expanse of space with my own eyes for the first time.
Such a profound moment for a kid.
Absolutely. I saw the moon in all its cratered glory, and it was mesmerizing. But what truly fascinated me was the twinkling stars and the inky darkness that stretched beyond the farthest star I could see. I remember thinking even then, what if each star is another world, another universe unto itself? It was a child's whimsy, but isn't that what we're hinting at?
Indeed it is. In a way, each galaxy could be seen as its own little universe, with billions of stars and potentially even more planets.
Right. And in the same way that I couldn't see beyond the farthest visible star with my humble telescope, we're now finding that there is so much more than what we initially perceived with our cosmological understanding.
Yes, and taking your analogy further, just like how your understanding of what lies beyond your backyard expanded as you grew older and had access to better tools, humanity's understanding of the cosmos and its origins has also expanded over time thanks to advancements in technology and scientific theories like the cosmic inflation.
Absolutely. From my backyard to the cosmic microwave background, the journey of understanding our universe is truly a fascinating one. And just like my childhood self, we're still asking questions, still seeking answers, and still marveling at the mysteries that the universe holds.
So, let's delve deeper into how cosmic inflation solves some major puzzles that the Big Bang Theory couldn't quite explain on its own. Let's take the cosmic microwave background, or CMB, for example. We know that the properties of the CMB are uniform in all directions. Now, if we adhere strictly to the Big Bang Theory, this presents a problem, because distant regions of the universe haven't had time to exchange information with each other and influence each other's properties.
Right, so how does cosmic inflation tackle this?
Well, cosmic inflation proposes that the uniformity we see in the CMB isn't because these regions exchanged information, but rather because they all emerged from the same inflationary state. Similarly, the theory of cosmic inflation explains why our universe appears to be perfectly flat, and why there aren't any leftover high-energy relics from the arbitrarily hot phase that the universe would have undergone if the hot Big Bang truly was the beginning of everything.
Fascinating. But how does cosmic inflation build on the successes of the Big Bang Theory?
Great question. So, cosmic inflation not only reproduces the successful aspects of the Big Bang Theory, but it also provides explanations for the major physical puzzles that the Big Bang couldn't resolve. The theory of cosmic inflation paints a picture where the universe was filled with a type of energy, perhaps something akin to what we now call dark energy, causing it to expand relentlessly. And then, when inflation comes to an end, this energy converts into particles and antiparticles, marking the phase of the universe we associate with the hot Big Bang. But there's more. The theory also suggests that during inflation, quantum fluctuations in the fields have two effects. They create density and temperature fluctuations, and they generate a primordial spectrum of gravitational waves.
So these quantum fluctuations, they're essentially creating a blueprint for the universe as we know it?
Yes, they're setting the stage for the formation of galaxies in the cosmic microwave background. These quantum fluctuations during inflation get stretched across the universe. Then smaller scale fluctuations get superimposed on the older, larger scale ones, seeding the structures we see in the universe today. It's an intriguing and profound concept, to say the least. Now, let's consider the concept of superhorizon fluctuations. Essentially, there's a limit to the size that any structure in the universe can take on. This size is determined by the speed of light, the rate of cosmic expansion, and the amount of time that's passed since the universe began.
So these superhorizon fluctuations are structures larger than this limit.
Exactly. And without a period of cosmic inflation, the upper limit to that size is known as the classical horizon. However, the fact that we observe coherent structures in the universe larger than this classical horizon is one of the key pieces of evidence supporting the theory of cosmic inflation.
And this theory makes some pretty specific predictions about these superhorizon fluctuations.
You're right, it does. One key prediction is that these fluctuations should impact the universe we observe today in ways that differ from the predictions of the non-inflationary hot Big Bang, or in areas where the hot Big Bang makes no predictions at all.
So essentially, we're looking at the universe today and seeing the fingerprints of cosmic inflation.
That's an excellent analogy. Cosmic inflation, in a sense, set the stage for the structure and properties of the universe we observe today.
And this is the essence of why it's such a compelling theory. It not only explains the mysteries that the Big Bang Theory couldn't, but but it also makes specific, testable predictions.
Absolutely. It's the ability to make these testable predictions that separates a compelling scientific theory from mere speculation. Cosmic inflation certainly falls into the former category. Let's now delve into some of the distinctive predictions that cosmic inflation makes. One of these is that the fluctuations we see in the universe should be almost, but not perfectly, scale invariant.
Scale invariant? Does that mean they're the same across all scales?
Exactly. During most of cosmic inflation, the fluctuations that get stretched to larger scales have the same properties as new ones that appear later on smaller scales. But there's a small departure from this right at the end of cosmic inflation, just before it gives way to the hot Big Bang. This results in slightly different magnitudes of fluctuations on small scales versus large ones, a prediction that's been observationally confirmed. We also predict that the universe should be spatially flat to at least one part in a few tens of thousands, with density fluctuations being 100% adiabatic, meaning they maintain constant entropy.
And have these predictions been confirmed?
Indeed, they have. Measurements have shown the universe to be spatially flat to about 1 part in 400, the most precise measurement we've made thus far, and the density fluctuations are at least 98% adiabatic, as predicted. Additionally, cosmic inflation predicts that these temperature fluctuations we observe in the cosmic microwave background will follow a bell curve or normal distribution on all angular scales. And yes, this too has been confirmed by our observations. So it's like we're seeing the fingerprints of cosmic inflation in our universe today. Isn't that mind-blowing? Now, my audience, what do you think about this? Are you as amazed as we are? Are you intrigued by these discoveries, these records, these incredible facts about how our universe came to be? Don't forget to leave your thoughts and questions. Your curiosity fuels this podcast, leading us to delve into these tantalizing mysteries. Are you enjoying the content? If so, don't forget to show your support. Remember, every bit of support helps us bring more of these fascinating stories to you. We're loving these explorations, and we hope you are too.
You know, all this talk about cosmic inflation and how it shapes the universe we see today really takes me back to my childhood. I remember when I was just 8 years old, I had this massive jigsaw puzzle. It was a picture of the night sky, filled with stars, galaxies, and nebulae.
Sounds like a big task for an 8-year-old.
Oh, it was. It was so overwhelming at first. Each piece of the puzzle was tiny, and it was hard to see how they could possibly come together to form this incredible image on the box. But bit by bit, piece by piece, the picture started to come into focus.
And how does this relate to what we're talking about?
Well, it feels like the universe is this grand cosmic puzzle, and we're slowly but surely piecing it together. We've got lots of the border in place with the hot Big Bang theory, and now we've filled in a big chunk of the middle with cosmic inflation. Each new observation, each new measurement we make is like finding another piece of the puzzle, helping us to see the bigger picture.
That's a beautiful analogy. And just like with your jigsaw puzzle, we've got some pieces that we're not quite sure where they fit yet. There are still unanswered questions about cosmic inflation that we're hoping to answer with superior future data.
Yes, and I can't help but feel a sense of excitement about that. It's like when I was searching for a specific puzzle piece that I knew was there somewhere. I'm excited to see what we'll discover next.
Stepping back into the realm of cosmic inflation, there are still some unanswered questions. For instance, are there tensor fluctuations or primordial gravitational waves present within our universe? We are able to predict the spectrum of gravitational waves that should be generated by inflation, but the amplitude of the spectrum is highly model dependent. If the tensor spectrum has a large amplitude, then we should be able to observe it. Right now, our best constraints tell us that the amplitude is less than 0.036.
So we're still not sure about the presence of these primordial gravitational waves.
Exactly, and not only that, there are other mysteries too. The scalar spectral index, or n subscript s prime, is predicted by inflationary models to change with scale. This is similar to how a ball rolling down a hill can change its acceleration if the slope of the hill changes. The expectation is that n subscript s will run by a small amount, around 0.1%. Whether we'll be able to measure this running and its consistency with inflation's predictions is another question we're hoping to answer. And here's another thing to ponder. Is the universe's geometry exactly flat, or are there tiny departures from perfect flatness as inflation predicts? Although inflation stretches the fabric of the universe to be indistinguishable from flat, the quantum fluctuations imprinted during inflation can also imprint a non-zero amount of spatial curvature to it. And the amount of that curvature could vary from 1 part in 10,000 down to 1 part in 1 million. These are all fascinating questions, and the answers could profoundly deepen our understanding of the universe and its origins. But we'll need to wait for superior future data to potentially answer them. Can you imagine what we might discover? There are even more questions that arise as we delve deeper into this topic. For example, are there any scalar fluctuations that exhibit any amount of non-Gaussianity to their statistics? We do expect that eventually we'll find a small non-zero departure from a perfect bell curve to the temperature fluctuations that we see. Will the amount of non-Gaussianity agree with inflation's predictions, or will it be either too small or too large?
So it's not just about whether there are fluctuations, but also about the nature of these fluctuations.
Exactly. And then there's the question of whether there are any resonant features in the spectrum of scalar fluctuations. We expect the answer will be no, as inflation predicts. But as in all scientific endeavors, we have to look for the unexpected if we want to give nature a chance to surprise us. Making measurements sensitive enough to test these 5 hitherto untested predictions is undoubtedly ambitious. But when it comes to a question as important as where did our universe come from, not even making the attempt to find the answer may be the greatest folly of all.
It sounds like there's still so much we don't know. But with every new discovery, every new observation, we move a little bit closer to understanding the origins of our universe. And that's what makes this all so exciting.
Over the course of this episode, we've traced our understanding of the universe, from the time when we gazed at the stars in wonder to our present-day knowledge of cosmic inflation. We've explored how the universe rapidly expanded from a tiny point to an unfathomable expanse, creating the seeds for everything we see around us today. But as it often happens in science, each answer brings with it a new set of questions. The mysteries of primordial gravitational waves, the behavior of the scalar spectral index, and the true flatness of the universe are just a few of the puzzles we still need to solve. But remember, in the grand design of the cosmos, we're all just inflationary anomalies, trying to understand the infinite expanse we call home.
That's beautifully put. We want to thank you all for joining us on this journey through space and time as we unravel the mysteries of our universe. If you enjoyed this episode, don't forget to blast that like button, leave a comment, and share this with your friends.
We appreciate your curiosity and your thirst for knowledge. Remember, the universe is full of mysteries, and exploring them is a journey we're all on together. Until next time.
Goodbye, everyone. Stay curious.
Our journey today was guided by the insights from an article titled "The Biggest Questions About the Universe's Beginning," written by Ethan Siegel and published on the Big Think site on February 6th, 2024. For those wanting to dive deeper, we'll have the full URL in the description. Until next time, folks.